In part three of today's talk, we're going to talk about Alfred Russel Wallace, and he was a huge contributor as well to the development of biogeography as a discipline. And he was inspired, as many scientists were and still are, by the tales of discovery of Humboldt. And he was a contemporary of Darwin as well. And he, on his own, developed a concept of natural selection. And he corresponded with Darwin. And so, really, that he's not credited, but that correspondence between the two of them helped refine Darwin's theory of natural selection. Um, but and often Wallace is kind of left out of the picture. Now, unlike Humboldt and Darwin, he was not born into wealth. So he supported his travel by selling his collected specimens and by selling his books. And so the Melee of the Archipelago was published in 1869, and it's one of the most vivid travel memoirs ever written, and it's never been out of print since that time. I actually haven't read it, but now I'm thinking I might after researching this fellow. He also wrote a book called The Geographical Distribution of Animals, which, of course, this should ring lots of bells because that is really what biogeography is, and the Island of Life, which also, island biogeography, and that's something that you've talked about in the past, and we're going to expand on in this course as well, is a book that he wrote as well. So he was a very influential man, and also had to work to make his money and to sell his collections, and was a working man. So that he rose to such prominence during that time is pretty amazing. And this is a picture. He spent 12 years traveling in the South, and this is a portrait that was done of his travels down in the southern tropic regions. So one of his big contributions was this map that he created in 1876. And it's, again, a visualization, and it ties different species to specific regions of the world. And so we might call that now ecozones, because they're quite large areas that's covered. But it's broadly defined as 6 zoological zones with 24 subregions. So you can see that they're broken down within themselves. So if we look at South America here, you've got a 1 down here, and you've got a 2 up here. And so those would be the subregions, and you can see the other ones for yourself. And so you're looking at things like North America, the near Arctic, the neotropical, the Caribbean, and the rest of Latin America. A lot of these ecoregions are still used today. And so this map still holds up today, even though he didn't know anything about plate tectonics. He didn't know anything about phylogenics, which is a big thing that's been going on in biogeography for a while. He didn't know anything about satellite imagery or advanced statistics, spatial statistics to look at these things. And so that he was able to come up with these broad concepts and still be so right on with them without all these analytic tools that are used today is pretty amazing. Now, I put this in, and I've taken it from a textbook on biogeography, and it summarizes 17 of the most important contributions that Alfred Russel Wallace made. So some people call him the father of biogeography. And I'll let you go through these on your own, but I'll just point out a few of them. So we talked about uniformitarianism, but one thing that he added to that is that the processes that are acting today may not be in the same intensity. So he's saying they're the same processes, but sometimes they're more intense than others. And so you might get evolutionary leaps. or adapt change leaps that happen quickly as opposed to over long periods of time. I'll let you go through a number of these, and we'll come back to these as we're going through the rest of the course this semester and see whether or not these principles really stand up over time. One of the things I mentioned that he didn't have the benefit of, and that's the theory of plate tectonics. And if you've taken a course with me before, one of the first year courses, you know that I like the story of Alfred Wegner. And that's because he came up with the concept of the continents all being one mass continent, which he called Pangea, which means all Earth, and then eventually drifting out to their present locations. And so this is a diagram of that, and you can see Alfred there. He actually was a meteorologist as well as a geophysicist. And although other people had noticed some of the similarities or noticed some of the evidence that he used, again, he brought it together as one theory, so as one explanation. So he took all of these observations and pulled them together into a theory that he called plate tectonics. And he published that in The Origin of the Continents in the Ocean, a book that he published in 1915. So what evidence did he use? Well, the coastlines fit together, some of them, as like a jigsaw. And again, other people had noticed this specifically with this example of South America and Africa. I mean, it's pretty obvious that they fit together, and many people had commented on that before. But again, he brought it into an idea that was overarching. The other thing is geology. And so if you put the continents back together as they were at one time, you can see this mountain range that runs up the center here of this large landmass. And as the plates are pulled apart, you can see that the Appalachian Mountains in the eastern seaboard of the United States and through Canada into Newfoundland and Labrador, as well as through the British Isles and into the Caledonia Mountains up here in Scandinavia, are geologically the same, and they're all created by the same uplift processes. Glacial evidence, looking at the striation marks that were left on the Earth. And if you look at those striation marks, you can see that we had an ice sheet that was spreading out in all directions, that was centered over Antarctica, went into Australia down here, went into India, into Africa, into South America, and that these striations track the movement of ice and show the direction of the movement of ice. And you can see some of these striations in this image here. And so glacial evidence was one. Fossil evidence, and this is the big one for biogeography, is this fossil evidence. And so you have the same types of fossils that are bridging different continents. And the explanation for having those same types of fossils, it would be very unusual to have the same animals evolve on the same continents, on different continents, and be the same type of animal. Now, some of this evidence has changed, and the way that we interpret that is more with land bridges and some other things now, but it was part of his evidence that he used. So his theory was rejected, and unfortunately, it was soundly rejected, in part because he couldn't come up with a viable mechanism. And so what he came up with was that the continents had been pulled apart by centrifugal force. And that's the spinning of the Earth on its axes. And there were some people who were swayed by, the strong evidence that he had that this could be a possibility. But he it was wrong. The rotation didn't cause that. Some people tried to carry out experiments to show that. Part of it was that it was challenging the paradigm of the time. So we had overcome the idea that the climate remained static, that the geology remained static, that evolution, that animals and plants remain static, but it was still believed that the continents had always been in the same place where they were, and that it was impossible for them to move. How could they plow through the ocean floor was the big question. And so he was challenging the paradigm of the time. And that's another reason why it was largely rejected. Because as much as we say there's a paradigm shift, it takes a long time, and people are reluctant to let go of those old paradigms. And so it was largely ignored. However, it was picked up again when they started to map the ocean floor with instruments that they had left over from the First World War. And as they were doing that, they found anomalous things on the ocean floor. They found rocks of all different ages. They found that they had mountains underneath the ocean and deep valleys or trenches underneath the ocean. And they found this with sonar by sending sound down and getting pings back. And what they came up with, or what he came up with, was this idea of seafloor spreading, so that the seafloor was spreading apart and new magma was coming up to fill the void of that seafloor spreading. In order for the Earth not to just get bigger and bigger and bigger, you needed the continents to recycle again and to plunge back down in the earth and go through subduction. But now we had a viable mechanism for how the continents could have been pushed apart, and that was this seafloor spreading. So modern plate tectonics was born out of continental drift, but now we had a viable mechanism. And in geology and in other disciplines, this led to a flurry of new discoveries and theories and explanations for things that had been unknown for a long period of time. So what does plate tectonics have to do with biogeography? Well, plate tectonics talks about the separation of the continents, about the coming together of the continents, about connections of land masses that you wouldn't expect. It talks about mountain building by pushing up when the plates collide and smash into each other and buckle, like the Himalaya mountains or the Alps mountains, where you have volcanic islands like Hawaii and Iceland and other volcanic islands. You also have uplift islands that have just been pushed up by these tectonic forces. And so in biogeography, what that explains is distribution of species, or the separation of species, or the changes in environmental conditions. So when you have mountains uplifting, you change the flow of winds and moist air coming off the ocean. And so you have that falling on one side of the mountainside and you have a rain shadow on the other. So you start to get drought. So it's these kinds of things that really cause the Sahara Desert to become a desert over time. And things like that. But before, it used to be a lush tropical area. One of the things about distribution of species, just aside, my husband and I have been lucky enough to go down to Antigua, which is an island in the Caribbean, for a few years now. And we stay in an eco cabin, and it's really outside the whole time. The only thing that is inside is the bedroom itself, where the bed is, and the kitchen, everything's outside. So when I was looking at that on Airbnb, I called the person and said, like, how do you deal with animals? Because I'm thinking about coming from Canada, where we have raccoons, skunks, you name it, we have it. In other places, we have bears that are going to come and eat your food if you're outside. How do you keep your food safe from animals? And she paused and said, well, the birds might peck at your food if you don't put it in a cupboard, but really we don't have many animals that are endemic to the island because they're a volcanic island. Unlike some of the Caribbean islands that broke off from South America, like Costa Rica and places like that, that came with wildlife on them, really Antigua didn't have any native wildlife except for the birds that came by and some salamanders and things that came by. But all the rest of the animals have been introduced. And so there isn't really anything that's going to eat your food when your food is outside, except for the birds. And it's true, the birds do eat your food. But that was new to me. I'd never really considered an island that grew out of the ocean and had no natural animals endemic to it because of that. Here's another example, and that is the elephant. And so this is showing that we have different types of elephant and elephant habitat, and that we have the African elephant and we have the Asian elephant. At one time when these land masses were together, they would have been the same elephant. So they have a common ancestor. But as these geographical areas were pulled apart, the populations became isolated from each other because of the geographical barriers. They no longer mated and bred together. And so over time, they diverge from each other, become more adapted to the new environments that they're finding themselves. And so they develop related species and families, but they're very different and they've diverged from that common ancestor over time. Now, it doesn't have to be a landmass. It can be a mountain berry that's come up. It can be a seaway that's opened up. It can be rivers or mountain ranges. It could be a desert or some other hostile environment that species get separated from each other and then start to evolve separately. So that's it for what I would have covered on Friday. If there's anything that I can clarify, let me know. Wednesday and Friday this week, we will discuss the classification of biota. And in Friday's class, we'll review a bit of this biogeographic history together. And that's it for now. So I will be in touch with you again on Wednesday. Have a good week and enjoy week 2. Okay, bye.